Okay, so now we're going to talk about some other climate change effects that are going on today. Again, we're not going to talk much about going into the future yet. So these are some of the things we're going to talk about. Global phytoplankton decline, slowdown of the ocean currents, declining oxygen in the air and oceans, nighttime versus daytime temperature changes, hurricanes, mass extinctions, ocean acidification and death of coral reefs, methane levels, poleward expansion of the deserts, and tropical diseases. So I hope everybody took their meds before we started our show here. And so everybody is happy, or at least placid. Actually, this first one, though, this first little thing, is encouraging. So for a while, I had quoted this earlier work by Boyce et al., and he had found that there was a 40% decline in phytoplankton since 1950. And, that's pretty alarming, since phytoplankton accounts for almost half of the primary productivity of the Earth and supplies a lot of our oxygen, and of course is at the base of the ocean food chain. So that's pretty serious. But what happened was there was another group that had also been monitoring over time phytoplankton levels, and they said, well, wait a minute, 40%, that's just too big. That's not what our data is showing at all. We think it's only more like a few percent. Now, if this were politics or if this were religion, then what would happen is these two groups would be slugging each other in the face over and over, year after decade after century, and it would be nothing that you'd ever want to watch. Luckily, these guys are scientists. They actually wanted to know what the truth really was. So what did they do? They got together and they tried to figure out, well, so what are our differing assumptions? The methods were clearly different, and so the problem seemed like it might have to do with calibrations between these different methods. So Boyce was using Secchi disks, which are these white disks that you lower into the ocean, and then or any kind of water, and then you see the opacity of that water, most of which is due to plankton of some sort, or algae, things like that. And the other group was using different methods. So these groups got together. I'll come back to that. Okay, it's a great story. But first of all, let's point this out, how important it is that water actually has its densest, fresh water has its densest, not when it's coldest, but actually a few degrees above that. And then it begins to get less dense as it heads towards the state of being ice at 0 degrees centigrade. And then, of course, when it turns to ice, then the density drops quite a bit. Water is almost unique. In fact, it may be unique. I'm not sure. But it's just about certainly the only liquid I can think of that has that property, that it actually gets less dense when it freezes. And that's a very good thing, because then that means the ice will float. If instead it got denser, then what you'd have is water would freeze, drop to the bottom, leaving the cold air that's able to freeze water more still on the surface, and you'd progressively freeze the whole ocean solid. So that would not be a good thing. The fact that ice is melting, that ice is less dense, means that you have this cap on top, and then the water underneath has a bit of an insulating layer in the form of that ice, and can remain liquid, so all the life that's in that water can be happy. Now, seawater is not that way. Seawater does get denser and denser right up till the time it's ice. And it's ice at a colder temperature because it takes energy, it takes entropy change to exclude or extrude all of that sodium and chlorine. And so what you actually make with the ice is not frozen salt water, but more frozen fresh water, and then the salt is progressively left on top or somewhere else. Okay, so back to the work of Boyce et al. So they got together and they found out that indeed it was the Secchi disk data that wasn't calibrated well, And Boyce was quite honorable about that and said, "Oh, okay, made a mistake. Well, let's publish a joint paper." And this joint paper is actually superior to either of their separate papers earlier, and now provides a consensus, complete view of what we got. And so there are phytoplankton losses, but they're only over most oceans, and they're not very large. They're just a few percent. So you can see there are places, though, where there is phytoplankton gain. So the North Indian Ocean, actually, although it's a little controversial there, maybe since 1950 it's been going down, but at least it looked like it was going up there for a moment. Maybe more obviously, the South Indian Ocean clearly has increasing plankton. Northeast Atlantic as well. But most oceans show a decline. But it's just a few percent, so it's not as serious as we once thought. This is not happy news. This has been research ongoing that is getting worse and worse the more new papers come out. So the AMOC, the Atlantic Meridional Overturning Current, it's called the meridional current because the Atlantic pretty much is a north-south ocean with a little bend in it, and because the current goes one direction on the surface and it goes the other direction along the bottom waters. And they're seeing a consistent decrease in the strength of that current of about 3% per year. That's pretty alarming. That's enough to shut off the current in a century or so. So Stefan Rahmstorf's a pretty well-known expert in this area, and he's published a lot in this, and he's part of this newer group that's finding that this looks like a higher and higher danger than we had thought. Now, we know that there's a tipping point. It's caused by a critical salinity point where the current will actually stop. And in fact, we're already in a region where we have two stability points, and one is for the current to be what it is, so slow but still going, and then the other very stable state that it could be in is for the current to shut off completely. And this tipping point was first written about by Lenton et al. In 2008. And the earlier IPCC reports thought this was a danger, but maybe only 10% odds that this could happen in this century. Now it looks like the odds are much higher. So the probability of a tipping point now, which is a major reorganization of the flow, is between 5 and 40%. And that's if we have the strong global warming that actually does look like it's in the cards. It's certainly what we're on course for now. And even with significant improvements in our carbonization, by the time you put in the add-on effects from soils losing carbon and permafrost melt, it looks like 4 to 8 degrees is still quite possible and not unlikely at all. It's not a worst-case scenario by any means. So the probability was even estimated at between 20 and 65%. So now you're talking about roughly 50-50 odds for a shutdown of the AMOC, and if the AMOC shuts down, pretty much the whole global circulation is believed to be in danger of down. So here's the strength of the AMOC. It's continuing to decline. And then, of course, here we are today, 2020, and you can see the prediction is for it to continue to decline. There's a new array that is going up that is going to be helping us going forwards, a new array of measurement that is going to be telling us the strength of the current. So the existing array is down here, kind of in the tropical or almost subtropical waters of the Atlantic, but we have a new array going in that is up in Canada to England and just tipping under Greenland there, where that is a very important place to keep good track of. Okay, oxygen content. So oxygen content of the oceans and the air is dropping. More of our atmospheric oxygen is getting bound up with carbon to become CO2, and warmer oxygens can hold less dissolved oxygen, just as we saw that it could hold less dissolved CO2 as well. And so the oxygen content of the oceans is going down. The oxygen content in the atmosphere is going down. And that's despite the fact that higher CO2s are expected to increase plant respiration, plant creation of oxygen. But you've got to remember at night that plants actually consume oxygen, and so the CO2 levels are given back off at night. There is really a respiratory cycle that plants do, just like animals do. But it's a day-night cycle, not a moment-to-moment cycle. And I apologize for the quality of this graph here, but all you really want to pay attention to is that in the oceans, the oxygen level is declining. So this is an oxygen. Here, let me show this. So oxygen, that's the bottom one, so that's on the decline. And in the land, it's kind of constant. In the atmosphere, this is oh boy, I want to make sure I don't get this wrong. So this is the fraction of the total emissions that remain in the atmosphere of the land and the oceans. This is CO2. Sorry. I should have refreshed my memory before I started this again. Okay. Anyway, so CO2 in the atmosphere, as you know, is going up, and in the oceans, it's boy, you know what? The more I look at this, the more I realize I probably shouldn't. I don't want to say anything wrong, so I might have to look at this again. The ocean absorbs more CO2 and warms. It becomes less effective at soaking up additional CO2. Of course, we know that the CO2 in the ocean is causing rising acidification. So yeah, you know what? I'm going to just skip past one and go on. Okay, so this is now about nighttime versus daytime temperatures. I think we talked about this as well last time, but I want to mention it again here. So nighttime temperatures are observed to be rising faster than daytime temperatures. So they're both going up, but daytime temperatures are going up not as fast as night temperatures. And the reason for that is because daytime temperatures have a lag in them. So as the sun comes in, it warms the ground, and the ground warms up the atmosphere. And the hottest time of day, of course, is not when the sun is highest at noon. It's more like mid to late afternoon. And so the ground is still quite warm, and the differential is a maximum around sunset. And yet it is the impedance of the ability of the hot ground to radiate its infrared back to outer space that's what the greenhouse effect is all about. So since that's the problem, rising greenhouse effect, then it is nighttime temperatures which are not going to be able to cool as much as they used to. The daytime temperatures coming in is caused by the sun, and the sun's incoming radiation is not changing. So that's here. This is the DTR, daytime temperature range. This is the difference between day and night. And you can see with these several different studies that is below zero. In other words, the daily temperature range is decreasing. And yet at the same time, the daytime temperature is going up. It's just that the nighttime temperature is going up more. So this is bad. Ecologically, this is bad. So it is cold nighttime temperatures which in the past have been controlling things like pine bark beetles, and that's why we're having so much trouble with wildfires in California now, is that we have so many of our pine trees in the Sierras and elsewhere dying because of the pine bark beetles, which used to be killed in the winter and they'd have to start their growth cycle all over again in the spring. Now they're not getting killed, and so their populations are only settling back but not to zero, and then rising even more so in the spring and summer again. Of course, mosquitoes carrying tropical diseases like Zika and malaria and so forth, those are also rising. And again, because the nighttime temperatures used to be what limited them to get as far north as they are now. And then here's another study showing that there's trouble here because the ability of forests to hold CO2 is decreased when their nighttime temperatures are going up. So again, plants, including trees, will respire at night, and the warmer the night is, the more they will exhale CO2. So the net CO2 that they'll be able to hold will be going down. So this could cause forests to stop their net sequestering of carbon entirely in the future. Something I don't really see addressed when we look at those who are advocating for planting trees to try and solve our CO2. Well, planting trees versus not planting trees is definitely in the right direction, but it might not be as much help as you would think. And then this graph is just showing that the rising global heat in the ocean is primarily in the shallower layers. So at the shallow layers, which are most in contact with the atmosphere, now think of what that means. So now we have higher temperatures, higher humidity because of the higher temperatures, higher ability to accentuate convection at ocean surfaces. And as convection takes air upwards, it cools. It cools at the adiabatic lapse rate, which is stronger than the normal lapse rate. And that makes for a stronger temperature gradient in the atmosphere going up, and that makes for stronger storms. So that's the bottom line, is that we expect stronger hurricanes. Hurricanes are storms that arise over water. So that's the prediction. Are we seeing that? And the answer is yes. So this is past data, 1981 to 2007. And you can see that the maximum wind speeds, this upper line here is rising. So typhoons, which are Pacific hurricanes, different name, same phenomenon, are showing the same thing. And notice how during the hiatus period, when global temperatures were not rising much because the PDO was in a cool phase, and also because rising smog was inhibiting the ability of the sun to get to the ground and warm the ground. Both of those were in effect during this 30-year period here, as we talked about in the temperature regimes talk that I gave. And but since then, we're clearly on a rising scale here. And this is a powerful El Nino, 1998, and then a powerful rebound back down in the year after. So more powerful storms carry with it another prediction, and that is lower pressure at the eye of the storm. Again, stronger convection is going to cause stronger rise of air at the center of the storm, and that's going to lower the pressure because that air trying to get in is inhibited by the Coriolis force to get in, and so there's a bit more of a vacuum that is created at the center of the storm. And so that's exactly what you see here with the gray. So the gray is showing decreasing pressure in the centers of hurricanes over the last 60 years, just what we would predict. And the opposite effect during the prior years, when we had nowhere near as much global warming, in fact none at all in here, right up to about here, and then we had kind of a couple of different temperature regimes that we talked about earlier. But since we've gone into a pretty consistent rise in temperatures beginning about here, then you can see that these pressure numbers are clearly going down, causing stronger speeds. So another way to plot these things is to look at the area of total devastation. And you can see that the area of total devastation has been going up. Now this is not a hurricane, so when you have low pressure, strong low pressure systems that form over land, we call that a tornado, and they tend to be much smaller in size, although the winds tend to be much more intense. And we'll talk about those a little bit later, I guess. So here we're back to hurricanes. So this is the number of Category 3, 4, or 5 tropical storms. And so you can see in general there's been a rise, but during the PDO minimum that we had after the great El Nino of 1998, you can see that they kind of stopped rising, and then when the new El Nino, very strong El Nino, came in 2015, 2016, then that carried with it also very strong storms. So clear correlation between storm strength and temperatures at the ocean. So stronger winds, higher humidities, deeper hurricane pressure gradients. No surprise we're seeing storms of unprecedented power. Hurricane Harvey in 2017 delivered not a once in a century, but a once in 25,000 years, once in 250 centuries deluge to southeast Texas. And what's interesting is that we had a once in 500 year storm in the same area 1 year before. And then we had another once in 500 year storm in the same area 1 year before that, in 2015. But our attention spans as humans is short, and so most people, except if you live in Houston, I suppose, have kind of forgotten about that. But nature someday is going to come after you, and then you probably won't forget it. Monster storms growing more common, hurricane category 2, 3, 4, and people are beginning to argue that maybe we should go to a magnitude 6, category 6, because category 5 we're bumping up against the top of the stated criteria for that range. Okay, what about tornadoes? Well, let's look at tornadoes. It's not so clear whether tornadoes should be getting more powerful or not, since they happen over land. But here is something that's statistically pretty significant, and that is that the tornado frequency has increased in the Midwest and the Southeast. At the same time, it's decreased some in Texas, Oklahoma, and Kansas, but the increase is much stronger. And so there is a net increase. There's certainly a net increase, but it is also moving east. The areas of strongest tornadoes are moving east. And that has to do, I guess, with the distribution of wind speeds. Okay, so now we're moving out of storms and we're talking about other effects of global warming. So one of them is that simply our domination over other ecosystems is going up at an incredible rate. As recently as 1900, wild vertebrates made up 50% of the total vertebrate biomass on land. Now only 3%. Humans and livestock today make up 97% of all vertebrate biomass on land. So if you took all of the vertebrates, including lizards and snakes, the little guys as well as the big ones, us and cattle and so forth, and you pile them up and you divvy them between wild animals and then humans and their livestock and their pets, I suppose, then what you'd find today is that the pile that is due to humans is almost all of it. The wild animals are a tiny little bit. So I suppose the message here is you will be assimilated. If anybody remembers the old Star Trek Borg, 40% of the primary productivity of the entire planet has now been diverted to one single species, us. People of some political bent might think, well, only 40, so we got 60% less that we can exploit. 60% left that we can exploit. That wouldn't be my response, but I think it would be some. So here's terrestrial vertebrate biomass. And notice the global carrying capacity has been going down. And that's because as we grow our presence on the land, the ability of the land to regenerate is going down. We'll talk more about that when we get to the future. World population since the birth of, since caveman days 10,000 years ago, emerging from the Ice Age. Relentlessly going up, except for the Black Death and the domination of the New World, North and South America, which brought with it plenty of new diseases that those populations couldn't handle. So that does show on a log plot here as a dip. This is just the last 1,000 years, not the last 10,000. So again, you see the plague and the Black Death here. So we're adding 1 billion people every 13 years at the moment. So clearly that's unsustainable. We're far past the sustainability of the planet right now, and so that will level off. And I fear that it will level off in a overshoot and crash catastrophic way and not through wise planning. Human extinction, probably not in the cards, but extinctions of other animals, well, it's happening at an incredible rate, even greater than the rate at which human population is growing, because the rate of human population growing is only part of it. It's the wealth that those humans want, which cause greater domination of the land, takeover of land, takeover of niches, takeover of resources that other species need. And I'm sure you've all heard about corals, the tragedy going on in the tropics due to rising water temperatures. So there's two ways in which corals suffer from climate change. One is that the rising temperature of the water causes the corals to lose their symbiotic algae. The algae are the ones that make the corals so colorful, and which produce the oxygen and other nutrients for the coral polyps. Rising acidity is hurting the ability of these corals, mostly made of aragonite, to pull CO2 out of the ocean and create calcium carbonate, which is their skeleton. So they're both less able to produce their skeleton, and they're less able to eat because the algae that help them are driven off with the high temperature water. So coral reefs, which are incredibly beautiful if you've ever seen them, mostly due to the algae and to the incredible different varieties and shapes with which they colonize the water, are disappearing. Rising acidity of the oceans is expected to kill all aragonite corals by 2050. 83% of the original Caribbean coral reefs have already died. Coral reefs are primarily in the tropics, where the water temperature is the warmest and where it will exceed the ability of the algae to tolerate quickest. In 2016, the record heat wave due to the El Nino caused huge losses in the northern Great Barrier Reef. The northern part of the Great Barrier Reef off Australia is the warmest part. It's the largest coral reef in the world, by far, bleached white. So the bleaching happens when the algae that are the symbiotic species that live with the coral leave. So the reef is not quite dead yet. Only 93% of the reef has been bleached as of 2016, mostly at the warmer northern end. But the bleaching happened again in 2017, and we expect that it's going to continue to reach further south to the cooler layers, cooler latitudes as global warming continues. So what happens when the corals die? Well, they're recolonized, but by different species on top, and then the coral underneath gradually dissolves and disappears, and then that won't even support these guys. So why haven't you been hearing about the Great Barrier Reef's imminent death? Well, many of you probably have heard of it by now, but there was a concerted effort on the part of the Australian tourist industry to keep this out of the UN's chapter. So this is the Great Barrier Reef is one of the World Heritage Sites, maybe the most important. And Australia's Department of the Environment explained their move by saying that experience has shown that negative comments about the status of World Heritage listed properties impacted on tourism. Well, yeah. In other words, if you tell people the reef is dying, they might stop coming. So this is not something that's going to happen in 100 years. This is happening right now. We're losing them really quickly, much more quickly than I think any of us ever could have imagined. To lose coral reefs is to fundamentally undermine the health of the very large population, very large proportion of the human race, says Ruth Gates, director of the Hawaii Institute for Marine Biology. They populate a tiny fraction of the ocean, but they provide habitats for 1/4 of all marine species. It's not just Australia, it's American Samoa, Hawaii. Current extinction rates estimated about 1,000 times the normal historical background rate, rising perhaps to 10,000, according to DeVos et al. In 2014. Now, the total number of species and the extinction rates, I have to admit, are very difficult to calculate, so you can find different numbers, but clearly they're very high. 90% of all the large fish are already gone. It isn't just global warming, it's overfishing, maybe even more important. The death of the coral reefs, needed by half of all fish species at some point in their life cycle. They're dying due to CO2-induced ocean acidification and warming. And McClenahan et al. Has documented how coral reef systems have affected the size and species mix of fish using historical photographs from Florida. And so these are kind of, well, they're sad, but they're interesting to look at, so I'm going to show you these. So in 1956, look at the size of the fish they were still able to get off of Florida in the coral reefs there. 1957, 1965, clearly they're getting smaller. 1978, smaller. 1983, 2008, and today, increasingly, it's jellyfish that you pull up. Jellies are happy in an ocean that is depleted of oxygen because they have a relative advantage. Jellies need very little oxygen. They're not active animals that need a lot of energy to do what they do. Fish, on the other hand, are just the opposite. Fish need a lot of oxygen because they're very active. So people are trying to figure out what you do with increasing jellies. There are places that do eat them, some of the poorer Asian countries. And there's a company that's trying to make diapers and even tampons out of jellyfish. Yeah. Okay. Sounds like a marketing challenge to me. What about methane? So we'll have a lot more to say about methane when we get into the chapter on the future. but we want to at least mention that we're certainly seeing rising methane right now in the global atmosphere and in the Arctic atmosphere and Arctic lakes. So this is methane trapped in the ice in Arctic lakes. So where do you get methane? So methane happens when you take carbon, dead plant material, and you isolate it from oxygen so that it can't combine to make CO2. The carbon then will do the next best thing. It's sort of second choice in the mating exercise, and it'll find hydrogen. And carbon, with its 4 bonding sites mated with hydrogen, will give you CH4. That's methane. The methane is trapped underneath the ice in winter. And so one of the more dramatic sets of videos is from Katie Walter Anthony and her group. She's at the University of Alaska. And you poke a hole in the ice and you put a lighter to it, and the methane is pretty obvious because it makes a big flame. So methane, of course, is the same stuff you cook with if you have gas stoves at home. The methane is also generating large craters in Siberia. These are methane explosion craters. They're huge, some of them up to 200 feet across. These are ice climbers on the inside of one of those craters. Sampling the methane down at the bottom, 50,000 times normal methane levels. Now, these are pretty dramatic, but you have to admit when you calculate the numbers, it would take of order 1 million such explosions before they'd be dominating Earth's climate. However, while they're only recently discovered the fresh ones that are exploding, it's really because of the large increase in the temperatures in Siberia that are happening. We are discovering many more of them all the time. And the mechanism in which they form, so what happens is pingos, which are the cores of ice that are in permafrost, when the ice melts, so that's increasingly happening, it leaves a vacuum there underneath the soil. And as the water flows away into the groundwater, then it leaves a subsurface volume that's ready to be filled with carbon in the peat, in the permafrost that is now melting. The permafrost, as it melts, the carbon then combines with hydrogen to make methane, since it's still cut off from the atmosphere above by the overlying layers of ground. So it's cut off from oxygen. When the pressure gets too high, this explodes. So craters have been discovered so far that are up to 200 feet across. In 2017, we're discovering over 7,000 new domes filled with methane. And I want to point out that methane levels in the atmosphere are rising much faster than CO2 levels. So CO2 from pre-industrial times has gone up about 48%, a little less than 50%, a little less than half, again, as much CO2 in the atmosphere. But methane has gone up by a factor of 3, so we're talking 300% of pre-industrial. There are a bunch of arrows here just showing methane is a very active chemical. It goes into the atmosphere and it comes back out again as well. So mostly the coming back out is because methane will combine with oxygen, and in fact you know that already if you have a gas stove. You have your methane combine with oxygen very, very rapidly if you put a flame to it. It's highly temperature sensitive, but at average Earth temperatures, the half-life of methane in the atmosphere is roughly 10 or 11 years. It's slower, more like 12 years in the Arctic, but it's faster, more like 8 years in the tropics where it's warmer. So the sources of methane are fossil fuel production and use, so the mining of natural gas. There's plenty of leaks. In fact, there's way more leaks there than the industry will account for. And I have a feeling that this number is probably understated quite a bit because this looks like it was completed by industry. That's one of the things we'll talk about when we get to the future. Agriculture and waste. So if you bury agricultural waste, carbon, underground, under big piles, compost piles, you're cutting it off from oxygen, and that carbon will combine now with hydrogen, and it'll make methane. Wetlands, so again, you cut off the carbon by covering it over with water. There's increasing wetlands happening in the tropics because one of the consequences of global warming is increasing rain over the tropical areas. Mostly that's over the oceans, but some of it is over the tropical lands, and also we're building more dams, building more reservoirs for human use. And those are covering over vegetation that ordinarily would have been exposed to the atmosphere, and as it decayed it would convert to CO2. But now it's converting to methane, which is, I don't think I mentioned, but fresh methane is 100 times the global warming potential of CO2, pound for pound. Okay, now we talk about an entirely different effect, and that is the boundary between the three atmospheric cells that we talked about: the polar cell, the feral cell, and then the Hadley or tropical cell. So those boundaries are places where winds are going in opposite directions, and it tends to cause a high-speed interface, which we call the jet stream. So there's the polar jet stream, and there's the subtropical jet stream. And they don't go around in just a flat latitude line. They go up and they go down and up and down. Those are so-called Rossby waves, these waves patterns here. And one of the consequences of global warming is that the polar jet stream is getting, well, both of these jet streams are getting weaker, but especially the polar jet stream is getting weaker. And as it gets weaker, then it tends to have an amplified, I realize you're not seeing this, an amplified Rossby wave pattern to it. And so the cold air that should be around the poles can migrate quite a bit further south, down, for example, now into New England and the east coast of the U.S. So we've had some freak freezes in recent decades because of that. But we've also had alarmingly warm temperatures in the Arctic, even in the middle of winter, because the other half of the Rossby wave goes far north, all the way up here. So what we expect is both an increase in major droughts and also an increase in major floods. Both of those. And those are because the Rossby waves are getting more intense, and also because the Rossby waves are getting weaker, the storms that they guide are moving more slowly. So a storm migrates along the Rossby wave, but it migrates more slowly, and as it does so, then if you're over it, you're underneath it rather, then you're going to get more rain. So Houston has seen that now 3 catastrophic times in the last 5 years. So when the storms do happen, then rising humidity enabled by the hotter air, the Clausius-Clapeyron relation we talked about, together with a slower moving jet stream, causes huge floods, severe floods. Now here's another effect. If the temperature gradient between the polar cell and the feral cell is the cell that we live in, if the temperature gradient is weakening, and it is, because we have a weaker polar cell, because the poles are warming faster than anywhere else on Earth, then it's also going to cause the polar jet stream to not just have these more amplified Rossby waves, but they will also, in general, migrate north. Okay, so weakening jet stream means a meandering, longer-lasting storms and drought, but it also means that they will, on average, migrate further north. So we learned in the chapter on the major cells in the atmosphere of the Earth that the Hadley cell, the tropical cell, is driven by heat. It's driven by the heating that is maximum on Earth around the equator. And of course, global warming is only going to make that heating more dramatic because the tropics are not able to cool as effectively at night. And so what you end up with is the polar cell is expanding, and so the Hadley boundary cell, the subtropical jet stream, is migrating to the north because the equatorial cells, both the north and south Hadley cells, are strengthening because of increasing warming. So, how much? James Hansen says observations actually indicate as much as 4 degrees of northward shift has already happened. And you can hear that in this talk here that's linked. At 410 parts per million, of course this slide is now a year or so old, a couple of years old. We're at 416 parts per million today as I do this in April of 2020. We're 46% of the way towards a doubling of pre-industrial CO2. Observations are outpacing by 200% climate models' northward migration. That means a factor of 3. Rising open temperatures is raising the energy of the tropical cell by 570 billion watts per year since 1979. Combine that with a weakening cold of the Arctic, and this is causing a poleward migration as well of the polar cell boundary. So that means that the deserts, which are occupied by the place where air is descending, air from the Hadley cell descends at about 30 degrees latitude, and air from the Ferrel cell, which is kind of a ball bearing between the polar cell and the Hadley cell, is also descending, and descending air will warm and dry. So that's where the deserts are. Think of the great deserts in the world. Northern Mexico, Southern California, the Sahara, northern China. So these are places where and that region is going to be migrating north. Now we, of course, here in Santa Cruz, we live on the boundary between northern and southern California, and that's a dangerous place. So we are going to be seeing more dramatic climate change here in Santa Cruz than many places on Earth. It's because the deserts of Southern California are going to be marching north. Tropical diseases are spreading north, so as hotter temperatures rise in the tropics. Formerly tropical diseases are going to increasingly become temperate diseases as well. So we're talking about dengue fever, malaria, Zika, Lyme disease. So, of course, Zika is particularly tragic because it causes microencephaly and brain damage in the young. But I got to point out that it isn't just these tragic Zika victims who will suffer mental handicaps. We all will, and that is because rising CO2, there's another entirely separate effect now I'm going to. Rising CO2 causes a reduction in the ability of us to think along many different measures. So a doubling of CO2 will cause a 21% decline in decision-making ability and other factors we'll look at right here. So this is work by Sadish et al. In 2012. So basic activity level dropping as CO2 rises, crisis response dropping, information usage dropping, strategizing dropping. So just when we need it most to think clearly, we're going to find it increasingly difficult to do so. Bees are suffering as well. Protein content of pollen is dropping due to rising CO2. The nutrient value of all plants actually is dropping because of rising CO2. So while a lot of climate denialists would like to say that CO2 is a plant food, yes and no, it does help plants grow faster, and plants are growing faster, as long as the water and the temperature regime is still favorable to them. Then if you do nothing but raise CO2, you do tend to make bigger plants, but the nutrient value of what they produce goes down. That they don't tell you, but it's true. There's another effect which I think is underappreciated, especially by people who so strongly support the idea of letting our soils soak up more CO2, well, our soils are going to need us to just keep them from getting worse. So rather than us depending on soils to help us, it's soils that need our help. So the help arrow, I'm afraid, is going in the wrong direction. Our soils are suffering. They're outgassing 17% more each year. Excuse me, let's make sure we do this right. This is work by Crowther et al., finding we estimated that the carbon emissions from soil are going up approximately equivalent to 17% of current human global CO2 emissions. So every year, humans will emit a certain amount, and then the soil will be responsible for an extra 17% on top of that. So whereas at the moment, the U.S. is also 17% of total CO2 emissions, that's actually wrong. We're now only 13%. It isn't because we've done so much better. It's because Asia is now growing so fast that we are now responsible globally for only about 13% of total global emissions. I'll just say that as an aside. So rising seas are also compounding pollution because the barrier islands are being flooded and taken away by rising storms and by rising sea level. And so that's expected to cause a lot more loss of carbon that would have been going perhaps to burning and causing it to instead just leak into the environment. Okay, so that's it for current climate change effects. I've still got one more on deforestation, and so I want to do that one as well and get that one up on YouTube. But that's it for this one. So these are some of the summaries for these other effects. Okay, so I will sign on again shortly for my next presentation that I will post, and you guys can all listen to it at your leisure on YouTube.